Kutasov will continue to tell us about Branes and gauge dynamics.
Okay, so I started discussing last time the system of D4 branes on a circle with twisted boundary conditions in the limit where the Hooft coupling in 5 dimensions is large, the strong coupling limit. And what I said about this background is that it is confining. It describes a strong coupling limit of a confining field theory. And I mentioned one observable that checks that this is the case, the energy of a quark and an anti-quark pair separated by the distance L, which we showed goes for large L like this. It's linear in L, and we even computed the tension T0 that goes into this equation. And as I mentioned last time, what I'd like to do today is discuss 2 more probes of confinement that will show us that this background indeed does describe a confining field theory. And so the first probe of confinement that I will talk about is the finite temperature behavior. And in particular, the presence of a certain deconfinement transition. So in ordinary Yang-Mills theory, in Yang-Mills, we expect, there's a lot of evidence for a phase transition at a temperature which is of the order of the QCD scale, at which the theory deconfines. And what I'd like to investigate is whether such a phase transition is present in this model, and we will find that this is indeed the case. But in order to do this, we first have to figure out how to even deal with this issue. And the way we deal with this issue is, as was mentioned already in lectures here, is we take time to be Euclidean. So the sign over here is flipped relative to the usual Minkowski sign. And we also compactify it on a circle of circumference beta, which is equal to 1 over the temperature. And we give the fermions twisted boundary conditions around that thermal circle. So this is what we're instructed to do when we study finite temperature thermodynamics in field theories like Yang-Mills theory. And in our case, because we're dealing with the bulk description of this theory, so we have this higher dimensional space that is related holographically to the theory, we have to say slightly different words. So in the bulk description, what we want to do is calculate the gravitational path integral with the boundary conditions that we get from the field theory. So I will just pictorially denote it like this. If this is the u coordinate that goes to infinity at the boundary, we want x0 to be asymptotically a circle of circumference beta. And similarly, we want x4 to be a circle of the radius that I called r4 yesterday. So x4, as I mentioned yesterday, is identified with x4 plus 2 pi r4. we want the boundary conditions for fermions around both of these circles to be anti-periodic, as I mentioned yesterday and today. And other than that, we allow the bulk spacetimes to do whatever they want. So we sum over all spacetimes that have such asymptotics. And one such spacetime is, of course, easy to construct. We have that sort of cigar geometry that we discussed yesterday, where space terminates at a finite value of the u coordinate, and time can just be compactified, so the radius of the time direction will not depend on the radial coordinate u. And we can certainly take this background, plug it into the gravitational action, and compute its contribution to the free energy. But in fact, the semi-classical approximation to this gravitational path integral in particular involves summing over all solutions with this asymptotics. And as should be clear from this picture, there is another candidate solution where the two are flipped. After all, we have anti-periodic boundary conditions both in the Euclidean time direction here and along the spatial circle. So no one can prevent us from considering spacetime in which we have a cigar of this sort having to do with Euclidean time. Of course, it will terminate somewhere else because the value of this UKK, as we saw, had to do with the radius of the circle we're on. And if this is the kind of solution we consider, then the x4 direction will instead be just living on a circle with constant radius. So these are, at the very least, two solutions that we should consider expanding about when we compute the gravitational path integral with the boundary conditions in question. And maybe I should also write the formula for this ut here. You can get it, of course, from here just by replacing R4 by beta over 2 pi or whatever. It's equal to 16 pi cubed times lambda over 9 beta squared. And so these are two solutions that we should consider. And in particular, the free energy is going to be something like this. So e to the minus beta times the free energy, which is equal to the gravitational path integral, will be equal to some prefactor that has to do with fluctuations times e to the minus the action of this first solution plus some other prefactor times e to the minus the action of the second solution. So whichever of these solutions has the smaller action will dominate the partition sum and therefore the free energy. Now, as it should be clear from these pictures, for beta equals to 2 pi r4, the two actions have to be equal by definition because the two solutions are related by the interchange of Euclidean time and this x4 direction. So they could in principle be equal all the way, but they definitely have to be equal at this point here. And a calculation that I will not do here shows that, in fact, they're not equal all the way. For temperatures that are larger than this critical temperature related to R4, it is the second solution that has the lower action, whereas for temperatures that are smaller than this critical temperature, so we can call this beta critical, the action of the second solution is larger. In other words, for the high temperature regime, it is this solution that dominates the gravitational path integral, and at low temperatures, it's this one. It's sort of nice because the first solution is the one that connects smoothly to what we did at 0 temperature last time. And what we find is that there is a phase transition between the two, which is a strongly first order phase transition. Because the background that describes the thermodynamics changes by a lot at the critical temperature, which is equal to 1 over this beta sim, right? Actually, one sort of simple heuristic way of thinking about this is that it's always the case that the circle that's smaller chooses to shrink. Intuitively, it's very reasonable that if you want to shrink a circle out of the two, you would choose the smaller one. And indeed, when you calculate the gravitational action, you find that this is the case. I should also say that there are these divergences when calculating these contributions to the free energy or these actions that you have to worry about coming from the UV region. But these divergences, so divergences from the boundary u going to infinity, you can easily convince yourself have the property that they correspond to a temperature-independent contribution to the free energy. So if you just cut off the thing in some way at large U, you get an extra contribution, a contribution from that region, which is cutoff dependent, but it does not depend as a contribution to the free energy on the temperature. And so one simple way to get rid of this ambiguity is just to declare that the low temperature solution has free energy equal to 0, because remember, this is the term in the free energy that goes like the number of colors squared of the Young-Mills theory, and you expect the free energy at the low temperature phase to be independent of the number of colors as in the limit where the number of colors goes to infinity. And so if you fix this ambiguity by declaring that this one is 0, then you can just calculate the difference between them, and then this issue of the UV divergences disappears from the game. But again, since I'm not doing the path integrals, we don't need to worry about this too much. So this phase transition, I claim, is a deconfinement transition. So that was one comment. Second comment is that this is a deconfinement transition in the gravitational regime. And a very simple way to see that is to think about that Wilson line that we were talking about last time. So what I said to you last time is that the reason the Wilson line, the reason this energy of the quark-antiquark pair went like the separation had to do with the fact that square root of GTT times GXX, which determined the Nambu-Goto action, was finite at the extreme infrared region in the geometry. And here, this is not the case. Of course, GTT, the metric in the time direction, goes to 0 at the tip. And therefore, the energy of the quark-antiquark pair goes to 0 as the separation goes to infinity at temperatures at which this solution dominates at these high temperatures. And so the theory is indeed in a deconfined phase in this region of temperatures. Yeah.
Very specific to that particular background where you can kind of interchange one black hole.
Yeah.
Could you comment on what happens, say, in general you would expect something in between, some kind of...
Sorry, can you speak up? They comment on what?
So the comment that you have one picture or another, that you can sort of interchange them in different regimes, is specific to your starting point when you choose black to describe...
So for example, the fact that the transition happens at beta equals to 2 pi r4 exactly is specific to this background. Say, if you looked at the Klebanov-Strassler background, it would not be the case. Yes, of course. As I said in the beginning of my lectures, one of the reasons I chose this one is that it demonstrates a lot of these issues in a relatively simple context. So in general, so what is the general story with backgrounds of this sort? You have some radial direction. You have some cycle that shrinks smoothly to 0. And that cycle doesn't even have to be a circle. Say in the Klebanov-Strassler solution, it's some kind of two-sphere that's shrinking to 0. And every single step in what I described here is in general much, much more complicated. So for example, forget even about this exchange issue. Even the problem of just constructing the black hole solution in, say, the Klebanov-Strassler problem cannot be solved analytically, like I did here. There is, I think you probably are familiar with some work by Aharoni, Bushel, and people who solved essentially numerically this problem, and it's complicated. So if you wanted to do this exercise in general, what you would have to do is the following. You're given some background like this that looks like some kind of generalized higher dimensional cigar. You would have to solve Einstein's equations. I mean, this is all, of course, assuming that we are in the regime where we can use gravity. You would have to solve Einstein's equations to find the black hole solution in this background. That would be a hard step. Then you would have to compare the free energies that I called here S1 and S2, which is another hard step. And it is expected that you would have a transition of this sort in general, although I don't know of a proof. Actually, one of the reasons I'm going to talk about another interesting observable soon is that it gives very similar information, but in a much simpler way for more general background. So I certainly agree with the spirit of your comment that this case is much, much simpler than the generic background of this sort, which has some complicated cigars with complicated metrics, dilatons, and other things.
I have a question.
Yes.
In this example, the metastable solution persists for all values of the parameter. Is that true?
So you say in the regime, for example, where the action of this low temperature solution is larger, in the high temperature regime, you still have the solution.
Is that true?
I think
hit some other sort of spinodial point where...
I don't think it ceases to exist anywhere. Well, I guess the question is, are there tachyons, right? I mean, it certainly exists as a solution to gravity, but in principle, it's possible that there are instabilities. I don't remember whether there are or aren't. But it is a classical solution. The issue is the fluctuations around it. Okay, so I think this is what I wanted to say about finite temperature phase transition. So if there are any other comments or questions. Yeah.
So do you see that the Polyakov loop is expectation value is 0 in one case and an element of the center in the other case?
Well, I mean, here, of course, this is the limit NC goes to infinity.
Yes.
But I think, you know, whatever you're supposed to see in the large NC limit is seen here. I mean, I don't have time to discuss this, but I think part of it was discussed in Larry Yaffe's lecture. It basically has to do with the action of a fundamental string that wraps. Right, so this Polyakov loop, where is this picture, is a fundamental string that wraps the time direction, right?
Yes.
So you can calculate its action. But, well, let's talk about it maybe separately because I don't think I have much useful things to say about it. Okay, so this is what happens at finite temperature. And let me talk about a third probe of this and related backgrounds, which is the behavior of the entanglement entropy, which undergoes a similar phase transition and can be studied to some extent both in the field theory and in gravity. So the second observable I will discuss today is the entanglement entropy. And it's actually a subject that sort of is more, it's discussed more in the condensed matter community than by field theorists, but there was also some work in recent years by field theorists on this. And so let me first tell you or remind you how this thing is defined. So if you want to be concrete about it, for example, suppose you take three-dimensional space. I'm talking here about, in the language I've been using before, about this R3 out of the R3, 1 of the space-time, and just artificially split it into two regions, the inside between two plates. So here is one plate, which is just an R2 at a given value of some coordinate, let's call it x, and here is another R2 at some other value of this coordinate x, and the two are separated by the distance L. So let's call the inside of this region A and the outside of this region B. Now, you can ask if you have some theory like our Young-Mills theory or any other theory, it could be an Ising model for all I care, that lives on the space, and suppose you're in the vacuum state of that theory, so that if you were using the language of density matrices, you would just write a trivial density matrix for it. So this is the vacuum density matrix in the language of your quantum mechanics course. And you can ask, what would an observer that is living, say, in the inside region between the two plates and does not have access to any degrees of freedom that are living in the outside region see? So clearly that person would see a non-trivial density matrix, which is obtained sort of by definition by tracing over all the degrees of freedom that live in the outside region the trivial density matrix for the vacuum. And therefore, because that person would see a non-trivial density matrix, they would also see a entropy defined in the usual way as rho trace of rho log rho. Now, this entropy is, as I said, of a lot of interest to people from sort of quantum computing and various solid state disciplines, but field theorists have looked at it as well, and they found very quickly, like the first sort of 15 minutes you look at this, you realize the following two facts. So one fact is that this SA entropy, which of course is a function of the separation in this kind of geometry, is UV divergent. It depends on the UV cutoff, but it is UV divergent in a very mild way, in the same sort of way that the free energies we were talking about at finite temperature are UV divergent. But for example, the derivative with respect to L of this SA is finite. So just like the free energy is defined up to some infinite constant, the entanglement entropy, which is what this object is called, is defined up to an infinite L independent constant. The second thing you notice very quickly is that this SA of L is proportional to the volume of this R2. That is sort of not very surprising. And therefore, it's better to think about the entropy density. So from now on, when I discuss this object, I will be thinking about the object up to some additive L-independent contribution and dividing by the volume of the R2. Now, in quantum field theory, there are general results about this object in 1+1 dimensions and in free field theory in higher dimensions. In particular, in strongly interacting theories like the ones we're interested in here, it's hard to do these calculations.
Isn't the volume of R2 infinite?
Yep, that is true. Well, this is just the statement that this entropy is an extensive quantity.
Actually, for me, extensive when you expect the volume of R3.
Well, it's the volume of R2. Well, you know, so I guess if you want to be careful, which I think is what you're hinting at, I probably should compactify this on some enormous torus, calculate what I'm about to calculate, and divide by the volume of the torus. But it is important that this entropy is not, well, when people first looked at it, the reason they very quickly realized it cannot be the volume of R3 is because of a fact that I didn't bother mentioning, and that is that the entropy defined in the way I just defined it is exactly the same. You can easily convince yourself as if you do it the other way around. So if you are in region B and you don't have access to the information in region A, that entropy is the same. Or to say it in another way, these density matrices, rho A and the complementary one, rho B, have the same eigenvalues, except one of them typically is much larger and it has a lot of zero eigenvalues. So because these two entropies are the same, it cannot possibly be that, say, the entropy goes like the volume of this region or the volume of that region. They're completely different in general. And, but in fact, if you just start thinking about free field or oscillators, you very quickly realize that that's how it goes. So yeah, so I'm being maybe a little cavalier here. I'm certainly thinking about the entropy density per unit volume transverse to this separation. Now, so as I said, in field theory, it's usually hard to calculate this, but in theories that are large N theories of the sort we're discussing and confining, one can actually say a little bit more. And one can argue as follows. So as I mentioned to you yesterday, large N confining theories should sort of reduce in this limit of large N to just free field theories of the bound states. So in the limit NC goes to infinity, we just have a free field theory of the, if you wish, glue balls. And the only thing that you need to know about these glue balls is that they have a Hagedorn density of states, as I mentioned yesterday. So there is some power-like prefactor that I will not bother with times an exponential in mass, right? That's a formula that we already had here before. And in this situation, we can actually estimate this entropy just by taking the contribution of each free field and calculating it, something that was done already, and then just summing over all these free fields that we have. And this exercise was done. So Well, so for a single free field of mass m, we have this entropy goes like, you can check e to the minus 2ml. I mean, the exact formula is known. And then there is a prefactor here that I'm not going to worry about. Again, it's known. And this is all in the limit where the mass times L is much larger than 1.
This is the finite.
Yeah, this is, so the precise, so if you, well, the precise statement, as I mentioned before, is that d by dl of SA is equal to something that I didn't bother writing here times this. And if you want to go back to the entropy itself, just like the free energy at finite temperature, it's defined up to some here L independent infinite constant or UV cutoff dependent. So, so this is for a single field of mass m. And so the total entropy for a theory of this sort would be just given by the integral over all m's times the density of states times the contribution of a single one of those fields of a certain mass. And let's say that this integral, for whatever reason, is dominated by the large mass fields. Then it would go like the integral up to infinity of e to the power, just copy from there, beta h minus 2L times m times a prefactor that I'm, again, not going to worry about. So you see now what's going on here. First of all, the contribution of a single very massive field looks like its contribution to the canonical partition sum. And in particular, there is a kind of Hagedorn behavior for this entropy. When L is larger than beta h over 2, the integral converges at large mass. And this is why we focused on large mass in the first place. And for L smaller than this beta h over 2, we have a divergent integral, just like the behavior of the canonical partition sum for such theories. So in the temperature case, what we say at this point is that there is a first order phase transition at some value of the temperature that is slightly below the Hagedorn temperature, at which we go from a free energy that goes like 1 to a free energy that goes like nc squared. And so here we should use the same words. There is, in quotes, a phase transition at a value of L which is approximately equal to this critical L, which is the Hagedorn distance over 2. And of course, I say phase transition in quotes because it occurs as a function of this parameter L, and it does not correspond to any kind of real physical change. It's just the change in the behavior of the entropy. So, so we certainly expect that confining theories like pure Yang-Mills in the large n limit, as long as they have this behavior which we believe in, have such a transition in the behavior of this entanglement entropy. And you can ask the question, what happens in the gravity regime? So,
NC squared and 1?
yeah, so, well, if this was if this was just e to the minus beta h, e to the minus beta m, and this was the free energy or partition sum, then what you would say is that when the analog of L here, that would be beta in that case, is sufficiently large, this integral converges, and it's by definition of order 1. There is no NC in it. But in the regime in which the integral diverges, you would say it only diverges in the strict limit NC goes to infinity. For any finite NC, of course, as I mentioned yesterday, these Regge trajectories end at some point. And the NC squared is just what replaces this divergent integral when you replace the Hagedorn density of states by the real thing, which is the density of states of the Yang-Mills theory, which at any finite NC crosses over to something different at the finite value of the mass. So yeah, I guess if there are any other questions about the field theory part of this story, that's a good time. Yeah.
What's the physical meaning of this divergence? Is it when L is smaller than the size of the glue ball, so you just shouldn't be...
The physical, so there are two, you're not talking about this divergence.
No, I'm
You're talking about this one. What is the physical meaning of, well, I mean, I mean, somehow, I don't have a good intuition about this entanglement entropy in general, but somehow it appears that, so again, there are no physical plates here, right? It's just a formal exercise. So somehow when you try to bring these plates together closer than the size, the typical size of glue balls, the behavior changes in this way. It's not a divergence, of course, as I said, it's just a phase transition. You know, this is not, no. So this is not a divergence any more than the analogous quantity at finite temperature is divergent, right? The canonical partition sum or free energy is not actually divergent, right? It simply goes from going like number of colors to the zero for low temperatures to going like the number of colors squared for high temperature. This is what actually happens around the Hagedorn temperature. And the analogous thing happens here. So somehow, I guess the only thing I can't help you much with intuition, but it somehow seems that this entanglement entropy in such theories, when you bring the plates closer together, is sensitive to the gluons, whereas for large L, it's sensitive to the hadrons. This is basically what this equation is saying, and I'm not sure I can say.
It's strange because rho A is the same as rho B. So if you see on the outside, as L
Yes.
gets smaller,
Well, this is the
you
entanglement
go
between the
tracing
two.
over less and less. And as L
Yes.
goes to zero,
Yes.
entanglement entropy should be zero because you go back to the...
Well, but somehow this quantity is sensitive to both of them. Well, I don't, look, I don't have good intuition about this quantity. All I can report to you is what it's doing. But, I mean, somehow it doesn't matter whether the small space is the thing you're tracing over or the outside, or the other part. Right, so the question is what happens in the gravity regime when we try to do the same calculation. And actually, it's interesting because until rather recently, it was not known how to even do this calculation. And about a year and a half ago, there was an interesting proposal by two people in Santa Barbara whose names are well, so what we would like to do is find out what happens in gravity. And we're going to use a proposal for answering this question that is due to these two people. And their proposal was the following. Their proposal was that in order to calculate this same quantity in gravity, what you have to do is calculate something that I will call the area, in quotes, and divide it by 4 times the Newton constant, where the Newton constant is, is given by this. And the area requires a little bit more explanation. It's given by an integral over a certain 8-dimensional surface of e to the minus 2 phi times the square root of an induced metric. So we have to talk about this surface a little bit. If if I call this surface gamma, so gamma, this gamma is an 8-dimensional surface which in our case, I mean, it can be stated more precisely, but let me just say it in this particular case. So what does this surface look like? The whole surface sits at some constant value of time. So we're here in Minkowski time, and we're just fixing it. The surface gamma wraps that S4 that we had there. It also wraps the R2, whose volume I was dividing by all this time. And it wraps the x4 coordinate, this circle that we discussed before. And so these are 7 of the 8 directions of it, and it looks like a line in the ux plane. So here is u, and here is x. Again, remember, x is the coordinate along which these plates are separated. It looks something like this surface. It's given by some formula. U is a function of x, which approaches. So as u goes to infinity, this curve must satisfy the boundary conditions corresponding to the 2 plates. Okay, so basically, in words, you can say that this surface is some kind of 8-dimensional surface in the bulk that's pinned at the locations of these 2 planes on the boundary. Okay, so this whole picture is a picture on the boundary, and you can find a surface like this that protrudes into the bulk. And of course, u of x is supposed to minimize this area function. And the reason I'm putting area in quote here is because of this factor of the dilaton, which is actually non-trivial. And it doesn't really have the interpretation of an area. Now, well, yeah, so, well, I should, let me say, I'm not going to go into a lot of things here. This is a really fascinating proposal that I think there are a lot of questions about. It's certainly not any kind of D-brane, because if you wanted to interpret it as a brane, it would have a tension that goes like 1 over G string squared, whereas D-branes have tensions that go like 1 over G string. Furthermore, it looks like some kind of instanton in Minkowski time. And also, if it was any kind of brane, in other words, if you were writing an action, which is the Einstein action, plus this, then just the presence of the source for gravity here on this 8-dimensional surface would back react on the metric at leading order in the string coupling, and you would have to figure out what this back reaction is, which we're not going to do. We're just going to fix the background to be that one and study the minimal area surface.
What would it be in the ADS 5 as 5?
I'm sorry?
If you consider ADS 5 as 5,
Yes.
Can you do similar?
Yeah, that's actually the case they looked at in more detail. There, of course, this is not an issue, but you still have this factor outside. Essentially, in ADS 5 crosses 5, you would set this phi to 0 because the actual G strings are sitting outside. You would have a surface that wraps the S5 and is sitting at some fixed value of time and wraps a few of the directions of R3, and approaches whatever boundary conditions you want to impose on the boundary, say these kinds of plates. And so they did such calculations, and you get sort of sensible looking answers, which are actually not that dissimilar to the analogous calculations. It's weak coupling in n equal 4 Young Mills, but I don't have time to go into this. So no, it's not, I would say this, it's certainly not any kind of brane we know about. And moreover, it's not supposed to be any kind of brane because there's nothing there, right? These walls in the field theory are fictional. It's not like I'm supposed to, in the field theory, allow them to fluctuate and in any sense. And here, there are a lot of open questions about this prescription, but what is the motivation behind this prescription? Well, this is an interesting formula, right? I would say it in the following way. There is no proof of this formula. What is known for sure is that in any theory that is ADS3 cross something, this formula reproduces exactly the known result in two-dimensional conformal field theory. So in any two-dimensional conformal field theory, it's known how to calculate this object exactly. And this formula reproduces it, including the coefficient. So for example, this 4 here is important to get the correct answer that is known in conformal field theory. And of course, the good thing about the two-dimensional conformal field theory formula is that it doesn't depend on any features, right? Because a lot of times you cannot compare what you get in gravity in ADS3 to any kind of conformal field theory results because these things are typically related by deformations and you don't know how to do that. But this particular object does not depend on any deformations and you get the right answer. In ADS5, they got something that was sensible. I think the question whether this is correct or not, and even more importantly, how to correct it to subleading orders in the 1/NC expansion is open and interesting, and I don't have much to say about it. But it looks like it's correct, and what I will say next is more evidence that it's correct. So let me, I will not describe, so there's an exercise to do. You have to plug in this shape of the surface with that metric into here and find the minimal surface. So I'm not going to discuss the details of this. You get some differential equation, obviously, that you have to solve, and I'm not planning to solve it. So let me just tell you how the solution looks. So the kind of thing that is easiest to get out of the differential equation is after you minimize over all these shapes and you find the position of the bottom of this hypersurface as a function of the separation L, you can plot this, let's say like that, on the curve. And so obviously, this U star cannot be smaller than, excuse me, I called it UKK there. And what it looks like when you do the calculation is something like that. So let's think about what that means. First of all, this part of the curve is very sensible. What this says is that if you take the separation L to be very small, the minimal area surface sort of protrudes a little bit into the bulk, but it doesn't do much of it. So this U star is very, very large when L is small, right? So as L becomes smaller, this minimal area surface goes up. Conversely, when you start increasing L, this minimal area surface dips further and further into the bulk. That's sensible too. But then at some point, this is something like, I think, 1.2 of this UKK, you reach a maximum and it starts going down again. So in other words, there is no minimal area surface for L L's larger than a certain maximal value. And that at first sight looks like a disaster because it looks like there's no solution to plug into this formula. But in fact, it's clear what happens here. When this L reaches some maximal value, this curve just collapses. And so for L larger than L max, what really happens there in this UX plane is that we have sort of two of these curves that sit at fixed values of x and go down all the way to the bottom of this cigar. Now, this might look singular, but in fact it isn't, because all these things, remember, are wrapped around the x4 circle. So what you really have is a picture where, so there's another solution, in other words, that's not captured by this curve, which is a disconnected solution for this curve that just consists of two of these cigars, surface that's wrapped around x4 and the radial coordinate, one of them at one value of x and another one at another value of x, a distance L away. Okay, so this is just sort of two cigars like that. And from this point of view, these connected solutions that look like that have a sort of tube that connects these two cigars in some extra dimension that is difficult to draw on the board. So, so this is the kind of solutions you find in just solving these differential equations. But now, and this is similar to the kind of behavior we got in the thermodynamics case, but now we have to understand, just like we did there, which one of them is dominant. After all, the prescription that we're instructed to use here is to choose the minimal area surface. And so we have to compare the entropies of these two solutions and see which one is smaller. So, well, for this disconnected solution with the two cigars, clearly the entropy is independent of the separation because these two cigars don't feel each other. So this is the entropy of the disconnected solution. It's just a constant independent of L. And the entropy of this other guy, of the connected solution we were talking about here, turns out to go like this. And so this is some critical value that you can only find numerically. And the place where the solution ceases to exist is at a higher point here. So this is a situation of the sort you were talking about, where the solution, after it becomes metastable, also ceases to exist at some point. And fortunately, that point is higher than the point where they cross. And so what we get in the gravity solution is indeed a first-order phase transition again. At this critical value of this L. Now, so that's good. That's another observable in these theories that shows the right sort of behavior that we saw in the field theory should have a first-order phase transition, or a phase transition at some finite value of L. And we find that it indeed has such a transition in the gravitational regime as well. And I should say that this critical value of L is of the order of R4. So you get numerically something like this. So this is again similar to the fact that the thermal phase transition also happens in this sort of regime. So this is actually an observable that's of the same sort as the thermal partition sum, but as you see, it's much simpler. Modulo all sorts of issues like what does it actually mean it's just simpler to calculate. You do not have to find a black hole solution in some complicated geometry, like the Klebanov-Strassler geometry. You instead just have to find some minimal surface in an existing geometry. And it's just easier to analyze. Another thing that's interesting about this is that it's likely that just like the finite temperature transition, there is such a transition also at finite numbers of colors. So it's not just some artifact of the large n limit. And therefore, it would actually be interesting to compute this on the lattice. I mean, this entanglement entropy is something that certainly can be calculated on the lattice. It's a very sort of Euclidean kind of observable. And if it is really like the thermal partition sum, just by doing lattice gauge theory for NC equals to 2 or 3, one should find this transition also there. So it certainly deserves more work, and the questions that you raised before are very interesting. It's not at all clear how this object that somehow does not really have physical meaning gets replaced in the gravity regime by an actual surface that looks like it has translational modes that we're minimizing over. And it's actually not at all understood how to say, generalize this proposal beyond leading order in G Newton. So,
did anybody do strong coupling on the lattice?
excuse me?
Did anybody do strong coupling?
No, you don't. What I'm saying is that you don't need to do strong coupling. If you just take honest to God, SU3 gauge theory on the lattice,
Analytically, you could just do
No, I don't mean analytically. I meant just, trying to get to sort of just SU3 gauge theory from the lattice to the actual one, not some strong coupling version of it, which is dominated by lattice effects. And there I think I would expect this transition to occur just in the physical theory. And so I think that would be something that would be nice to understand. Okay.
Just in the
Yes.
definition of
Yes.
entanglement entropy,
Mhm.
because you were integrating, you were tracing over B,
Yes.
but of course this is a trace over states. Don't you need to localize the state? Which states are localized? Can all states be localized either in A or in B?
Well, so
The vacuum state isn't localized at all.
So one thing that you can do, I mean, so a concrete thing that you can do, say, suppose you have a free, like one thing that people like Mark Serdnicki and others have done many years ago is consider a free Klein-Gordon field, right? And so replace R3 by a lattice and think of the Klein-Gordon field just as a bunch of an infinite collection of coupled harmonic oscillators, one living at each lattice site. And you can discretize the Klein-Gordon action, and then you can put these walls wherever you want to put them, and the trace then would literally be a trace over the harmonic oscillators that you don't want to keep in a state like some ground state for the coupled harmonic oscillators. So it's certainly in a theory like that, where you put in a UV cutoff and have degrees of freedom living at fixed positions and coupled in some way, you can perform this trace. Right?
If you do something like that, wouldn't that imply certain boundary conditions of these surfaces? Which case makes it look a bit more physical.
Boundary conditions. I don't think so. Why? So think of a simple problem. You have two harmonic oscillators coupled, and you're tracing over one of them and getting a state for the other. Right. So this is a simple example of the sort of thing that is being done up on the top board. You're not really putting any special boundary conditions on these oscillators, right? You're just literally tracing over them.
One used thermal density metric to begin with.
Yeah, so of course, I should have mentioned probably that I've made choices here just to be concrete. You can calculate this entanglement entropy in any state you want, either pure or not pure, like the thermal state. And of course, I also made a choice of how to split the geometry. For example, you could just have a ball, and the two regions would be the inside and the outside of the ball. So I've made choices here, but these were convenient for what I was trying to do. And you can, of course, people generalize this construction to starting there with the thermal state. And I mean, in order to relate the entanglement entropy to sort of real entropy. But I don't think it's very well understood, at least by me, what all of this means. I mean, you know what it looks like to me is it's a little bit like in black hole physics, there is this membrane paradigm picture of the black hole horizon, where sort of from the point of view of a faraway observer, it looks like there's actually something there. And there is a more fundamental picture where there's actually nothing there as a solution of Einstein's equation. So this looks a little bit like, I mean, by this I mean this here, looks a little bit like the analog of the membrane paradigm picture for this case of the entanglement entropy. It looks as if there is an actual surface there. But there has to be some sort of more fundamental definition of this object which does not involve any special surfaces that are actually fluctuating in space, it seems to me. But anyway, I don't have anything to say about this, so maybe I should just... this is something that certainly I would encourage people to look at. I mean, this is a very interesting proposal, and if you have something useful to say about it, that would be good. So let me summarize this part of the discussion of pure Yang-Mills theory before moving on to introducing quarks into the game. So the main point of this part of my lectures was that we embedded 3+1 dimensional pure Yang-Mills into a larger theory, which has this parameter that we called lambda 4, the dimensionless 't Hooft coupling, which was the ratio of the 5-dimensional coupling and some compactification radius. And the picture that we found was one in which the confinement scale, and by confinement scale here, I mean one of all these things, like the mass of the lowest lying glue balls, the value of the temperature at the deconfinement transition, the value of this critical L, etc. It behaved as a function of this lambda 4 in some way like this, where at small lambda 4, where it really is Yang-Mills, it's exponentially small. And at large lambda 4, it just behaves like the Kaluza-Klein energy. This is the Yang-Mills regime, which we understand qualitatively but don't know much what to say about it quantitatively. And this is the supergravity regime, which we actually studied in detail in these lectures. So as we increase the size of the coupling, the confinement scale increases, and we can think of this lambda 4 as just governing the confinement scale. So the pure Yang-Mills picture and the place where we can calculate are sort of very different regimes. Now, of course, I assumed here that there is no phase transition in between those regimes. That's an issue that arose yesterday. And it's possible that there is one, but the three kinds of observables that we discussed here don't show any evidence of it. They're consistent with just smooth evolution between these regimes. And so that's basically as well as we can do at present, both in this background and in other confining gravity backgrounds. We can calculate in some regime which is relatively far from where we want to be, and then it's sort of an art to figure out what we can use out of these calculations quantitatively to learn about physics here. So any questions or comments about any of this? Okay, so the next thing I want to do is to introduce quarks. And of course, the main reason to do that is that a lot of the things that people are actually interested in QCD is the physics associated with mesons and baryons and not necessarily with glue balls. And so we would like to understand how to get those. And this, in this context that I'm discussing here, was proposed by Sakai and Sugimoto in 2004. And so I'm going to review these constructions and say a few things about it. So the basic idea is the following. And here are the NC D4 branes that we talked about previously in these lectures. And this, let's say this is the X4 direction that is compactified on a circle that we had. We want to add additional branes to the picture that sit at fixed values of X4. And they are actually 8-dimensional branes. So in order to have NF flavors of quarks, we would put NF of these D8 branes at some particular value of X4, and of course they're then extended in all the other directions. And similarly, NF anti-branes that are similarly extended in all directions other than X4, and are localized in the remaining direction. And there is now a new parameter, which is the distance between the branes and the anti-branes along the X4 circle. And it's pretty easy to see if you just follow your nose that the new states we have introduced, at least at the massless levels, are just left and right-handed quarks, or fundamental fermions under the gauge group SUNC. So there are now two new kinds of states. There are the 4-8 strings and the 4-8 bar strings that stretch between these kinds of branes. And the 4-8 strings give rise to massless left-handed fermions. And then, of course, some tower of massive states that we're not discussing. Whereas the 4-8 bar strings give rise to right-handed fermions. And so we are now in a position to study the theory which also has these fundamental representation fields. Now, this construction has actually manifest in it the chiral symmetry UNF left times UNF right, which in the gauge theory is just the symmetry of performing unitary transformations on the left-handed quarks and the right-handed quarks separately. And here it just comes from the unitary groups acting on the D8 branes. So there is a natural UNF gauge group acting living on each of these D8 branes, and these fundamentals, Q left and Q right, are also fundamentals of the respective gauge group. So this is not only a construction that gives us the fermions, it also gives us naturally the chiral symmetry that we're very interested in QCD. Now, so now we have to basically repeat what we did in the case without these quarks, in the case where we do have them. And before, we made a point of studying the dynamics as a function of this dimensionless coupling lambda 4. And now we have two couplings that are dimensionless that we can vary, which are lambda over R4 and lambda over L. So we can ask what happens to the dynamics of this theory as we vary these couplings. I should probably emphasize that we take here the number of lasers fixed in the limit where the number of colors goes to infinity, so that we can really think about this picture with deep branes and don't have to worry about the back reaction, at least at leading order in G string. Now, so the question is, what does this new parameter do for us? We sort of understood in the previous discussion what this parameter does. As we vary it, we get stronger and stronger confinement. The scale of confinement of quarks becomes higher and higher as we increase the coupling. So the question is, what happens as we increase this second coupling, lambda over L? This is the more detailed version of this question that I want to analyze. And so clearly, so one way to do this, for example, is fixing everything else, just bring the two kinds of D branes closer and closer together, these flavor branes and anti-branes. We can, by bringing them closer together, increase this parameter. And so we will have to discuss this in detail next time, but clearly, qualitatively, without even doing any calculations, one thing that is clear is that it somehow has to do with the interaction between the left and the right-handed quarks. So one way of thinking about it is if you take this separation to be very, very large, if L is large so that this parameter is very small, then these quarks interact with each other by exchange of 4+1 dimensional gauge fields that have to propagate a very long distance, and therefore the interactions between them, between the left and the right-handed quarks, are very small. Whereas if you bring the two plates closer and closer together, the strength of the interactions between them increase, and we might expect non-trivial dynamical effects, such as breaking of this chiral symmetry, generation of a mass for these fermions. And so even before we start doing any calculations, it's natural to expect that this lambda over L is going to be a parameter that is going to determine the strength of the interaction between the left and the right-handed quarks, and therefore the dynamically generated mass of them. And indeed, when we analyze this background better next time, we will see that for large lambda over L, this chiral symmetry is broken to the diagonal subgroup, and the fermions Q left and Q right get a mass. Precisely the kind of thing that happens in QCD, but we will do this exercise in, again, just like here, in a different regime where we can do it in gravity. But I think I probably should stop here and continue next time. Well, it's so one way of thinking about it is the following. Well, let's see. Maybe I should be probably looking at this. So we have here one kind of branes that. So these strings go between branes that are stretched in these directions and branes that are stretched in those directions. And what we need to do is see how many Dirichlet-Neumann directions there are. How many directions of space have the property that they are Dirichlet on one side, but the boundary conditions are Dirichlet on one side and Neumann on the other side of the string. This is, if you look sort of at the textbook analysis of boundary conditions, the relevant issue, because for every direction that is of this sort, Dirichlet on one side and Neumann on the other, there is essentially a sort of twist field that you have to add to construct the ground state of the string, and that bumps up the mass. So here, if you look at how many Dirichlet-Neumann directions there are, so all these strings are stretched in 0, 1, 2, 3, but all the other directions are either Dirichlet on one side and Neumann on the other, or vice versa. So there are 6 Dirichlet-Neumann directions. And what that means is that the Navesh-Ward sector strings are massive, because one thing that you probably remember is that, say, in the D0, D4 system, where there are 4 Dirichlet-Neumann directions, they are exactly massless. So if there are more than 4 Dirichlet-Neumann directions, they're massive, the Navesh-Ward sector strings, and vice versa. If there's less than 4, they're tachyonic. So here, in other words, sort of a simple analysis of this sort, maybe if you didn't follow, it doesn't matter, because the basic thing I wanted to say is that this is the kind of analysis that you need to do, and it leads you to conclude that the Navesh-Ward sector open strings are massive. But the Ramond sector strings are always massless. That's some feature of just having a Ramond ground state. And so the Ramond is massless. So in other words, there is, in fact, a massless fermion that you get from there. And the only thing that you really need to worry about is why is it chiral in 3+1 dimensions. And that's something that requires a few lines of algebra. But it's basically just an open string analysis. I don't know of any sort of qualitative reason without doing it. To see. Another way to answer this question is that if you put these things on circles and T-dualize a few times, you can relate it to other systems that you might have seen. And there it's known that what you get from here is just chiral fermions, but in 4 dimensions.
Any other questions? Okay, let's thank David again.